Welcome viewers, in this video we will see the details about two-port network. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, an introduction to the two-port network. First we will see what is the network. Generally any network may be represented schematically by a rectangular box. Normally it is represented by rectangular box, any network. A network may be representing either a source or load or for a variety of purpose. So normally it is referring the either source or load or some variety of the purpose. A pair of terminal at which a signal may enter or leave a network is called a port. So the port is nothing but the pair of terminal at which the signal may enter or leave. The network is called a port, right? Now we'll see the further detail. A port is defined as any pair of terminals into which energy is supplied or from which energy is withdrawn or where the network variable may be measured. So the port is nothing but the pair of terminal. It can be energy supplied or energy withdrawn or variable can be measured. Now we'll see the diagram having the one pair of terminal and two pair of terminals. So refer this diagram. This is the network having one pair of terminal, 1 dash. One such network having only one pair of terminals, 1 dash as shown below. So this network having only one pair of terminal. Now refer this diagram. This is two-port network. Two pair of terminals are available, 1 dash, 2 dash. So this is called a two-port network. Normal network having one pair of the terminals. This 1 dash refer the input terminal, 2 dash refer the output terminal. So it can be used for further analysis. Normally all the networks are represented. This electronic system, communication system, transmission are represented by two-port network. So having one pair of terminal, 1 dash is called a network. Having two pair of terminals called a two-port network. One side refer input terminal, other side refer the output terminal. Now we'll see the further detail. A two-port network is simply a network inside a block box. Inside a block, and the network have two pair of accessible terminals. Usually one pair represent the input and other pair represent the output. So one is representing input and other is representing the output. Now such a building block is very common in electronics system, communication system, transmission and distribution system. Figure B shows the two-port network or a two-terminal pair network in which the four terminal having paired into ports 1 dash and 2 dash. So the figure B refer the two-port network. Four terminals are referred. It is grouped as 1 dash for referring the input, 2 dash referring the output. Now we'll see the further details. The terminal 1 dash together constitute a port. Similarly, the terminal 2 dash constitute another port. So that we have two ports, 1 dash and 2 dash. Two port containing no sources in either branch are called a passive ports. Among them are power transmission lines or transformers. So the sources not available mean that is called a passive port. Two port contain the sources in their branches is called a active port. Sources available mean it is called a active port. A voltage and current assigned to each of the two ports. So in two ports we are assigning voltage and current. Input voltage, input current, output voltage, output current, like that. The voltage and current at the input terminal are V1, I1. Whereas V2, I2 are the specified at the output port. So V1, V2 refer current and voltage in input port. V2, I2 refer voltage and current in output port. It is also assumed that the current I1 and I2 are entering into the network at the upper terminal 1 and 2 respectively. So I1 and I2 is entering the port in 1 and 2. Right. Now we'll see the further detail. The variables of the two-port network are V1, V2 and I1, I2. Two of these are dependent variable and other two are independent variable. Right. So based on the assumption, two are independent, two are dependent. The number of possible combination generated by the four variables taken two at a time, that is 6. Thus there are 6 possible set of equation describing the two-port network. Right. So the number of possible combination generated by the four variable at two taking 2 at a time, that is 6 possible combinations are 6 set of equations are represented by the two-port network. So in this video discuss the introduction about the two-port network. What is network? What is two-port network? What are the variables are available? Which are independent and which are dependent? And how many equation we can frame? From this 4 variable we can frame the 6 set of network, 6 set of equations. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the open circuit Z parameter, open circuit impedance Z parameter under two-port network. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. And I will go to the topic, two-port network. In that open circuit impedance Z parameters. The Z parameters of a two-port network for the positive direction of voltage and current may be defined by expressing the port voltage V1 and V2 in terms of current I1 and I2. So we are going to give the Z parameters for the two-port network. The voltage is expressed in terms of current. V1 and V2 is going to express in I1 and I2. V1 and V1 is nothing but input voltage, V2 is the output voltage. Similarly, I1 is the input current and I2 is the output current. Here V1 and V2 are dependent variable and I1 and I2 are independent variables. The voltage at the port 1 dash is the response produced by the two currents I1 and I2. Now we'll refer the two-port network circuit diagram, the block diagram. So this is the two-port network. We know that two-port network is nothing but having input port and output port, defining the current and voltage at input side, current and voltage at the output side. So this I1 and V1 refers the input voltage and current. I2, V2 refers the input current and voltage, I2, V2. So this is the 1 dash. This is referred as 1 dash. This terminal is referred as 2 dash. And this is 1 dash. This will be 2 dash. And this is 1. So input port is termed as 1 dash. Output port is termed as 2 dash. So here we are going to give the voltage V1 and V2 in terms of current I1 and I2. V1 equal to Z11 I1 plus Z12 I2. V2 equal to Z21 I1 plus Z22 I2. I will take the equation number 1 and 2. In matrix form we can write this is the voltage matrix V1 V2. So this is nothing but a impedance matrix Z11 Z12 Z21 Z22. And the current matrix I1 and I2. So this is expressed in terms of a matrix. Now we'll see what is this impedance. Z11, Z12, Z21 and Z22 are the network functions and are called as impedance parameter. Impedance Z parameters. So voltage is expressed in terms of current. In that we are having the impedance parameters Z11, Z12, Z21 and Z22. Right. Now we'll see these details about the impedance parameter. The individual Z parameter for a given network can be defined by setting each of the port current equal to 0. By making the port current equal to 0, we can define the impedance parameter. That is making the current, first making the output current 0, then input current is 0. So that we can define these impedance parameters. So first we will see suppose the port 2 dash is left open circuited. The output port 2 dash is open circuited, so that current is 0. So by making the output port left open circuited, I2 is 0. With this I2 equal to 0, we can define the Z11 and Z21. These two parameters can be defined. Now we'll see the detail. So Z11 equal to V1 by I1. In that I2 is 0. That is output port is kept open, so output current is 0. So what is Z11? Z11 is the driving point impedance at the port 1 dash with the port 2 dash is open circuited. Right? Driving point impedance. It is called as open circuit input impedance. See that V1 I1. So Z11 that refer input out open circuited input impedance at the input side. So that it is called a Z11. And one more parameter Z21, that is V2 by I1. By making the I2 equal to 0, output port is open circuited, so current I2 is 0. So here refer V2 by I1. So output port voltage divided by input port current. So what is this? Where Z1 is the transfer impedance at the port 1 dash with the port 2 dash is open circuited. So it is also called open circuit forward transfer impedance. So we are referring output port to input port V2 by I1. Output port voltage divided by input port current. So that it is called a open circuit forward. Similarly reverse available. Forward transfer impedance. So now we define Z11 and Z21. Now we'll see the remaining two impedance parameters. For the next two parameter, suppose that port 1 dash is left open circuited, then I1 equal to 0. For first two parameters, we open circuited the output port 2 dash, so that I2 is equal to 0. For remaining two parameter, we are making 1 dash. Input port is open circuited, so the input current I1 is 0. With that, we can refer Z12 and Z22. What is Z12? V1 by I2. See the input voltage V1, input port voltage V1 by output port current. So this is also a transfer. Earlier we discussed forward transfer impedance. So this is the reverse transfer impedance, input to the output side, where Z12 is the transfer impedance at the port 2 dash with the port 1 dash is open circuited. It is also called open circuit reverse transfer impedance. We already discussed forward transfer impedance. This is reverse transfer impedance Z12. And the another parameter is Z22, V2 by I2. Both voltage and current refer the output port. So this is nothing but open circuit output impedance. I1 V1 by I1 is input port impedance. Input open circuit input impedance. This is open circuit output impedance V2 by I2 by making I1 equal to 0. Where Z22 is the open circuit driving point impedance at the port 2 dash with the port 1 dash is open circuited. It is also called the open circuit output impedance. So now we define the four parameters. Z11 in a open circuit impedance parameter, Z22 open circuit output impedance, then Z21 is forward transfer impedance, Z12 is reverse transfer impedance. So within that we can go for a equivalent circuit. We can able to draw the equivalent circuit of this two port network by referring all this impedance. So this is the equivalent circuit of two port network governed by the equation 1 and 2. Earlier we have two equations, that is open circuit impedance parameter is shown below. So this is the input port 1 dash, output port 2 dash. Input current I1, output current I2, input voltage V1, output voltage V2. So this in Z11 is nothing but the open circuit input impedance available in the input side. Similarly, Z22 is the open circuit output impedance available in the output port. Similarly, we have the transfer impedance are available. So Z12 is the reverse transfer impedance, open circuit reverse transfer impedance. Similarly, Z21, here I1 is there, Z21 into I1, that is the forward transfer impedance, right? So the reverse transfer impedance refers input voltage V1 by I2. This forward transfer impedance refers I1 and V2 by I1, right? So we have all the parameters: input voltage, input current, output current, input impedance, output impedance, reverse transfer impedance, reverse forward transfer impedance. So this is the equivalent circuit for a open circuit is a parameter. Now we'll see the further details. If the network under study is reciprocal or bilateral, then in accordance with the reciprocity theorem, V2 by I1 with I2 equal to 0 can be written as V1 by I2 when I1 is equal to 0. That is Z21 equal to Z12. In case of bilateral, then the reciprocity theorem we can write like this: Z21 and Z1 both are equal. It is observed that all the parameters have the dimension of impedance. Moreover, individual parameters are specified only when the current in, we'll see the detail. So current in one of the port is 0. So in this open circuit impedance parameter, we are making any one port is open, then the current in the port is 0. This corresponds to one of the port being open circuited, from which the Z parameters are derived. The name is open circuited input impedance, right? So we are making any one port is open circuited, the current is 0, then we derive this impedance parameter, so that it is called a open circuit impedance parameters. So in this video we discussed the two-port network under that open circuit impedance Z parameters, that we are making the any one port is open circuited so that the current is 0, then we derive the four impedance parameters: input impedance, output impedance, forward transfer impedance, reverse transfer impedance. From that we drawn the equivalent circuit also. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we'll see the solved problem based on the open circuited impedance Z parameter coming under the two-port network. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Solved problem 1. Open circuit impedance Z parameter. We know that Z parameter is a open circuited. We are keeping the two-port network. One port is kept open and the parameter is fine. Z parameter is fine. That is Z11. That is a input open circuit input impedance. Z22 is the open circuit output impedance. Z21 is the open circuit forward transfer impedance, transfer between input and output. Similarly, Z12 is the open circuited reverse transfer impedance. These four parameters we need to find: Z11, Z22, Z12, Z21. Now we'll refer the diagram. Find the Z parameter for the network shown below. So this is the network given. The three impedance available: ZA, ZB, ZC. So these are coming under two-port network. A dash is the input port, plus minus. A dash is the input port. B dash plus minus is the output port. V1 is the input voltage. I1 is the input current. V2 is the output voltage. I2 is the output voltage, I2 is the output current. So based on that we need to find the four Z parameters. First we will frame the equation from this given network, then we'll find the Z parameter. So in that, first we need to, when the port B dash is open circuit, we know that it is a open circuit input impedance. That is, we are going to keep the any one port is kept open, then the remaining values are calculated. First we will keep the output port B dash, we are going to kept in the open circuited condition. So when it is open circuited, the I2 is 0, right? Because of open circuited impedance, the output port B dash is open circuited, so the I2 is 0. There is no current because of open circuit. The current will flow through ZA and ZB. ZC is not taken into account because current will not flow. So the total impedance is ZA, ZB. From that we can frame the equation. First we will find the V1. So the V equal to I into R. So V1 equal to I1 into R value, impedance ZA plus ZB. So V1 equal to I1 into ZA plus ZB. So very simple formula. V equal to I into R. So V1 equal to I1 into ZA plus ZB, because these two are connected in series. Then what about the V2? V2 is nothing but voltage across ZB, right? So what is the current flowing through this? I1. So I1 into ZB, right? So V2 is nothing but voltage across B dash, that is nothing but voltage across the impedance ZB. ZC current is not flowing, not taken into account. So across ZB the current flowing is I1 and the impedance is ZB. So V equal to I into R. I is I1, R is ZB. So we framed equation 1 and 2. Now let us name the numbered as equation 1 and 2. V1 and V2. By keeping the B dash open circuited, I2 is 0. Now we'll go to the input side. When the port A dash is open circuited, so that I1 equal to 0. Now we are going to keep the input port A dash is 0. So that I1 is equal to 0. Now the current I2 will flow through ZB and ZC. Current is not flowing through ZA, not taken into account, right? Current is flowing through ZC and ZB. Now first we will find the V2. V2 is nothing but the current I2 into total impedance. I2 into ZB plus ZC. V2. Right. Then what about V1? V1, this is an open circuit, so no current is flowing. So V1 is again nothing but the voltage across ZB. So current I2 into ZB. So V1 equal to the current I2 flowing through ZB into the impedance ZB. Right. So is numbered as equation 3 and 4. V1 equal to I2 into ZB. V2 equal to I2 into ZB plus ZC. Now we can, from these 4 equations, we can find the Z parameter one by one. The circuit in this problem is a T network. So the generalized equation is V1 equal to Z11 I1 plus Z12 I2. Z11 is open circuit input impedance. 11 refers input impedance. Z12 is the open circuit reverse transfer impedance, transfer between input and output. Similarly, one more equation, V2 equal to Z21 I1 plus Z22 I2. Here the Z21 is the open circuit forward transfer impedance. Z22 is the open circuit output impedance, because 2 refers the output port, 1 refers the input port. Right. Now we need to find the value of Z11, Z12, Z21, Z22. Now we'll see this one by one. So we already have the 4 equations are already available. From the 4 equations we can easily find these values. So Z11, when the port B dash is open circuited, I2 equal to 0, generally Z11 equal to V1 by I1. I2 is 0. Input voltage divided by input current, so that it is called a open circuit input impedance. So V1 by I1 is nothing but Z11. So from equation 1, V1 equal to I1 ZA plus ZB for the given network. This is general formula, this is given network. Now brought that I1 in the denominator this side. So V1 by I1 equal to ZA plus ZB. So this V1 by I1 is nothing but Z11. Z11 V1 by I1. So for this given network, in open circuit input impedance Z11 equal to ZA plus ZB. Right? So we are easily calculated the input open circuit input impedance. Similarly this side, when the port AA dash is open circuited, then I1 is 0, Z22 equal to V2 by I2. Right? Output voltage divided by output current. So from equation 3 we can easily calculate. Equation 3 is V2 equal to I2 into ZB plus ZC. Brought that I2 in the denominator this side. So V2 by I2 equal to ZB plus ZC. So V2 by I2 is nothing but Z22. Open circuit output impedance. So Z22 equal to ZB plus ZC. Right? So Z11 is calculated and Z22 also calculated. Now we'll go to the remaining. I will say we will go to this side. Again, B dash is open circuited, I2 equal to 0. So that Z21 equal to V2 by I1. Output voltage by input current. This is called a open circuit forward transfer impedance. Transfer means output by input, V2 by I1. Here both are input, here both are output. So that is called a input impedance, this is output impedance. This is transfer impedance, forward. Now how to calculate this? Now we'll refer the equation 3. We'll refer the equation number 3. 3 is nothing but V2 equal to I1 ZB. Brought this I1 in the denominator this side. So V2 by I1 equal to ZB. V2 by I1 is nothing but Z21. General formula, this is based on the network. That is ZB. So open circuit forward transfer impedance Z21 equal to ZB. Now we'll come to this side. That is port AA dash is open circuited, I1 equal to 0. In this case Z12 equal to V1 by I2. Input voltage divided by output current. Here output voltage by input current. So this is the open circuit reverse transfer impedance. So this can be calculated from equation number 4. V1 equal to I2 into ZB. Brought that I2 this side in the denominator. So V1 by I2 equal to ZB. V1 by I2 is nothing but Z12. That is equal to ZB. So Z21 also ZB, Z12 also ZB. So both are same. So the network is bilateral network, reciprocity. So we can conclude that this network is a bilateral network, this is a reciprocity. So in this we calculated the Z parameters for the given network. First we frame the 4 equations. By keeping the output port open, we framed 2 equations. By keeping the input port open, we framed another 2 equations. From these 4 equations, we can calculate Z11, Z22, Z21 and Z12. One by one we calculated. And also it is concluded this is the bilateral network, reciprocity network. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we'll see the solved problem based on the open circuited impedance parameter, Z parameter. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Open circuited impedance parameter, Z parameter, solved problem 2. The problem is find the Z parameter for the circuit shown below. So for this network, we need to find the Z parameters. So what are the Z parameters? Z11, V1 by I1 by making I2 equal to 0. That is open circuited. Open circuited means in this network, this is the input port A dash. This is the output port B dash. Current I1, voltage V1 at input port. Current I2, voltage V2 at the output port. So first we are making the output port is open circuited. So that I2 equal to 0. By keeping I2 equal to 0, we can find Z11 and Z21. Z11 is nothing but open circuited input impedance V1 by I1, referring the input parameter. Z21 is the V2 by I1, output port voltage by input port current. So that it is a open circuited forward transfer impedance, transfer between input and output. And another 2 parameter, we are making the input port is open circuited. so that I1 equal to 0 for these two cases. For that we can find Z22, V2 by I2, open circuited output impedance, referring the output parameter V2 by I2. Z12 equal to V1 by I2, input port voltage divided by output port current. So this is the open circuited reverse transfer impedance. So these four parameters we need to find. For the first two parameter, we are making the output port is open circuited. So I2 is 0. For the remaining two parameter, we are making input port is open circuited. So the input current I1 equal to 0. So this is the network available. 1, 2, 3, 4 resistors are available. 1 ohm, this is 2 ohm, this is another 2 ohm and 4 ohm. So voltage V1, I1, V2, I2. So first we will find the parameters one by one. First we will find Z11, open circuited input impedance, Z11, V1 by I1, I2 equal to 0. What is I2 equal to 0? When I2 equal to 0 means V1 can be expressed in terms of I1 and the equivalent impedance of the circuit looking from the A dash terminal. So I2 equal to 0 means this port, output port is open circuited. We can refer from the input side, right? So V1 equal to voltage across the input port and I1 is the voltage in the current in the input port. So the V1 can be equal to I into R, that is V equal to I1 into Z impedance, Z equivalent of this circuit. We'll see the after making A dash equal to open A dash by making B dash open circuit, we can see the equivalent circuit. So this is the equivalent circuit by making B dash is open circuited, right? So only A dash is considered. These four resistors are available. So in order to find the V1 equal to I1 into Z equivalent. So V1 equal to I1 into Z equivalent. So we need to find the Z equivalent of this circuit, so that we can easily find V1 equal to I1 into Z equivalent. So Z equivalent is nothing but we are referring from this end, A dash. So while referring this end, what happened? This 1 ohm resistor is available. So here the current is divided, so that these two branches are parallel. Same current is flowing through 4 ohm resistor. That means these two are in series. So these two are in series, that is parallel with this 2 ohm resistor. That is in series with the 1 ohm resistor, right? So 2 and 4 are connected in series. So 2 plus 4, 6. That 6 ohm is parallel with 2 ohm. So that is given here. For parallel combination, R1 into R2 divided by R1 plus R2. R1 is 2 ohm, this 2 ohm. R2 is 2 plus 4, 6 ohm divided by R1 plus R2, 2 plus 6. So this combination is in series with the 1 ohm. So 1 plus. So 1 plus this combination, 2 into 6 divided by 2 plus 6. So 1 plus 2 into 6, 12, 2 plus 6, 8, right? So 12 by 8 is 1.5. So 1 plus 1.5 is 2.5 ohm, right? So the Z equivalent of this circuit. From this Z equivalent, we can easily find V1 equal to I1 into Z equivalent, V equal to I into R. Z equivalent is 2.5. Now brought this I1 in the denominator, V1 by I1 equal to 2.5. This V1 by I1 is nothing but Z11. This Z11. Z11 is nothing but V1 by I1 by making I2 equal to 0. So that V1 by I1 is replaced as Z11, that is equal to V1 by I1, that is nothing but 2.5. So that Z11 equal to 2.5 ohm, right? So this open circuit input impedance is calculated by making the output port current 0. In order to find the V1 equal to I1 into Z equivalent, we are calculating the Z equivalent of this circuit referring from A dash. From that easily we can calculate the Z11, that is 2.5 ohm. Now we can find the Z21 for the same circuit. The same circuit we need to find Z21 by referring the output side. Now refer this circuit. Z21 equal to V2 by I1 by making I2 equal to 0. So what is V2? V2 is the voltage across 4 ohm impedance. So this is a 4 ohm. This is the original circuit. This output port is open circuited. We need to find V2. V2 is nothing but voltage across this 4 ohm resistor. How will you find the voltage across this 4 ohm resistor? V equal to I into R. So we need to find the current flowing through this 4 ohm resistor. R is nothing but 4 ohm. Right? So V2 equal to Ix into 4. V equal to I into R. R is 4 ohm. Ix. Ix is the current flowing through this 4 ohm resistor. This Ix. This I2 is already 0. So our aim is we need to find the current flowing through this 4 ohm resistor. Now refer this. This is a V1. Current I1 is flowing. Input port current. Current is divided here. At this point current is divided. Current is divided to 2 ohm resistor. Another current is divided to this 2 ohm and 4 ohm are connected in series. So 6 ohm resistor. The balance current will flow through 6 ohm resistor. So one branch is 2 ohm resistor. Another branch is 6 ohm resistor. So by using the current divider rule, we can easily find the current. Well, let us consider this is Ix. Current flowing through this branch is Ix. We need the current flowing through this branch only, not this branch. So that we are making Ix. So I1 is the total current. Ix is the current flowing through this branch. This is the what we need. So Ix equal to, what is the current divider rule? This is the branch current equal to total current I1 multiplied by other branch resistor. What we need the current through this branch. But here numerator what we have, other branch resistor 2 divided by total resistor 2 plus 4 6. So 2 plus 6. Right? In voltage divider rule, branch voltage equal to total voltage multiplied by branch resistor divided by total resistor. Same branch resistor. Where we need the voltage, that resistor is multiplied. But in current divider rule, it is opposite. Right? We want the current through this branch, mean it is multiplied by other branch resistor 2 divided by total resistor. So I1 equal to 2 divided by 8. So that is nothing but 2 divided by 8 is 1 by 4. So I1 by 4. So Ix equal to I1 by 4. Current flowing through this 4 ohm resistor is I1 by 4. Now we'll go to this. V2 equal to Ix into 4. V equal to I into R. R is 4 ohm. I is Ix. Ix what we calculated? I1 by 4. This 4 got cancelled. I1. V2 equal to I1. Brought this I1 in the denominator. So V2 by I1 equal to 1. So this V2 by I1 is nothing but Z21. Open circuited forward transfer impedance. That is equal to 1 ohm. Right? So Z21 we calculated 1 ohm. Right? By using the current divider rule, current is calculated. From the current, the impedance is calculated. So the one part is over. By keeping the output port is open circuited, we calculated Z11 open circuit input impedance and Z21 open circuit forward transfer impedance. Now we'll go to the next part by making the A dash is open circuited, so that we can able to find the remaining two impedance parameters. When the port A dash is open circuited, the voltage at the port B dash can be expressed in terms of I2. So while making the port A dash is open circuited, automatically I1 is 0. So we need to express in terms of I2. And the equivalent impedance of the circuit is viewed from B dash. Here we viewed from A dash. Now we need to go with B dash. I1 is 0, I2 is calculated, and the impedance calculated from B dash. Now we'll go to the next step. We'll see what is the equivalent circuit while making A dash is open circuited. So now we'll find the remaining two impedance parameter. First we'll find Z12 V1 by I2 by making I1 equal to 0. V1 is the voltage across 2 ohm impedance, and let the current in 2 ohm impedance is Iy as shown in the below. So I1 is 0, V1 by I2. So we need to find the V1, voltage V1 we need to find by referring this diagram. This input port is open circuited. This output port, the voltage is V2, B dash, the voltage is V2. What is V1? We need to find V1. Then only we can find Z1. V1 is the voltage across 2 ohm resistor. So V equal to I into R. I is current flowing through this 2 ohm resistor, IY into R is 2 ohm resistor, right? So V1 equal to IY into 2. So now we need to find the IY, current flowing through this 2 ohm resistor. Current will not flow through this 1 ohm resistor because of open circuit. Again here we are following the current divider rule. Here I2 current is there, this current is divided at this branch. Part of current is flowing through 4 ohm resistor, remaining current will flow through this branch, 2 plus 2. They are connected in series, so 2 plus 2, 4 ohm resistor. One 4 ohm, another branch also 4 ohm. So we can apply the current divider rule. IY, branch current equal to total current multiplied by other branch resistor. So this is the other branch resistor, 4 ohm. So what we need is this branch resistor, but it is this 4 ohm resistor. We can write like this: 4 divided by total resistor, 2 plus 2 plus 4. So the current divider rule opposite. What we need is branch current through this 2 plus 2, 4 ohm. So it is multiplied by numerator multiplied by other branch resistor, 4 divided by 2 plus 2 plus 4. So 4 divided by 8, that is nothing but 1 divided by 2. So IY equal to I2 divided by 2. So now we calculated I2, IY, current flowing through the 2 ohm resistor. So V1 equal to I1 into 2 based on the formula V equal to I into R. But IY is I2 by 2. This 2 got cancelled. So V1 equal to I2. Brought this I2 in the denominator, this side. V1 by I2. That is equal to 1. V1 by I2 is nothing but Z12. So Z12 equal to 1 ohm. So the open circuit reverse transfer impedance Z12 is 1 ohm. So earlier Z21 also 1 ohm. This Z12 also we got 1 ohm. So now we got one more parameter, Z22. We'll see the Z22. So the another equivalent circuit is available. So this input port is open circuited. We need to find the output port voltage V2. What is Z22 is nothing but V2 by I2. V2 by I2. V2 equal to I2 into Z equivalent. We need to find the Z equivalent of this circuit so that we can easily calculate the Z22. What is Z equivalent? We need to refer from B dash. Already A dash is open circuited. So we need to refer from B dash. So what is that? So at this point the current is divided. So this 1 ohm is not taken into account because of open circuit. Current will not flow through this. So current is divided means these two are in parallel. This 4 ohm is parallel with this branch. These are connected in series, 2 plus 2, 4. So this 4 ohm is parallel with this 4 ohm. Right? The current will not go here. So 4 ohm resistor and 2 plus 4 ohm resistor both are in parallel. So Z equivalent equal to 4 into 4 divided by 4 plus 4. R1 into R2 divided by R1 plus R2. 4 into 4, 16 divided by 4 plus 4, 8. So 16 by 8, 2 ohm. Z equivalent equal to 2 ohm. So V2 equal to I2 into Z equivalent. V2 equal to I2 into Z equivalent is 2 ohm. So brought this I2 in the denominator, this side. V2 by I2 equal to 2. So V2 by I2 is nothing but Z22. Open circuit output impedance. That is 2 ohm. Now we calculated all the 4 parameters. Z11, Z21, Z12, Z22. Right? All 4 impedance parameters are calculated. So we can go for the general equation and general conclusion. Here Z12 is equal to Z21. Both are 1 ohm, what we calculated, which indicate the bilateral property of the network. Because both are equal, this is a bilateral property. The describing equation for this 2-port network in terms of impedance. I will write the impedance, the generalized equation, right? So because of both are equal, it is a bilateral property. The given network is bilateral. The general equation is V1 equal to Z11 into I1 plus Z12 into I2. Similarly, V2 equal to Z21 I1 plus Z22 into I2. So V1 equal to Z11 is 2.5 ohm into I1 plus Z12 is 1 ohm, so into I2. And V2 equal to Z21 is 1 ohm, so into plus I1 plus Z22 is 2 ohm to I2. So V1 equal to 2.5 I1 plus I2, V2 equal to I1 plus 2 I2. So this is the generalized equation. So in this problem we calculated the Z parameter for the given network. Four impedance parameters are we calculated. For that, first two parameter calculated by making output port is open circuited. Remaining two calculated by making input port is open circuited. And we concluded that this network is bilateral because both are equal. Transfer impedance are equal. And also we framed the general impedance equation for the network. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.